So today we'll continue our discussion of syntax-directed translation. And with syntax-directed translation, what we are doing here is that we have the grammar, and in this grammar we add what we call embedded actions. So these are the actions that we embed into our grammar, and these actions will get executed when? When will these actions get executed? Yes?
When it's parsing?
Okay, when it's parsing, but at what point in the parse, during the parse? Yeah.
During the reductions.
Yeah, exactly. Whenever it makes a reduction. So whenever a reduction happens, whenever this reduction happens, we will execute this action. And this reduction may happen multiple times during the derivation, and it may happen at different levels. So this can happen multiple times. Okay? This is assuming an LR1 parser that parses in a bottom-up manner. So if we look at this at this example string, by the way, maybe we should do a little bit of tracing of the parsing of this string. This is what we have in the stack. Initially the stack is empty, and this is the string, and this is the action. So initially we have a or x equals a times 3 plus b. This is our string, and our stack is initially empty. Now we will not show the building of the LR1 tables and all of these details, but we will assume that we have an LR1 parser that is working correctly on this. So now on this LR1 parser, what will be the first step here?
Shift.
It will shift. So after it shifts, we will get x here, and we will get equals a times 3 plus b here. Now x is an identifier, so x is an, this is an identifier, this is a number, this is another identifier, a number, and another identifier. So now what will it do? Will it reduce at this point? Will it reduce this to identifier and then identifier to factor? No, it will not reduce. How will it know not to reduce here? Of course, we are not showing the LR1 parsing details, but how will it know not to reduce, that it needs to shift, not to reduce? Yeah, the look ahead, exactly. So there will be a rule, to reduce by rule 10. The reduction by rule 10 will not have a look ahead of equal. It will have a look ahead of something that follows a factor. And what follows a factor is a multiply or an add, or it could be an end of file. But a factor is never followed by an equal. Okay? So that's why from the look ahead, so there will be somewhere in one of the states, there will be a reduction, factor identifier, but the look ahead for that will be anything that follows the plus, minus, multiply, divide, but it will and it will not have or end of file, and it will not have an equal. So in this case it will just shift again, and when it shifts we'll have x equals, and that will result in another shift. Then the other shift will put the x equals a. Now what's the action? Now what's the right action? So will we reduce this x equals a? Does this match anything? By the way, you can replace x with an identifier. So do we have x equals identifier somewhere here? No.
Yeah, no. What about at 1? No, so look at
No, not yet.
Okay.
So what is reducible here is, this is an identifier. We can reduce an identifier to a factor. So what will happen here is that it will reduce the identifier to a factor. So it's going to reduce by rule number 10. Reduce 10. And this is going to give us x equals factor. Then factor can be reduced to a term. So, by the way, we are here. In this derivation tree, we are identifier to a factor. Then factor gets reduced to a term. So then we reduce by rule number 7. And this is going to do x equals term. And we still have multiply 3 plus b. Now, term, will this term get reduced to an expression at this point?
No.
No. It will not reduce the this term to an expression. Why? Because of the look ahead. We have a look ahead of multiply. An expression cannot be followed by a multiply, because a multiply can appear in the middle of an expression. An expression may be followed by close parentheses, but it may not be closed by a multiply. The multiply will appear in the middle of an expression. It will not follow an expression. So here, we will not substitute expression for term. We will just shift. Here, we're not showing the LR1 details, but we are assuming that we have an LR1 parser that is working correctly on this. So it's going to shift x equals term, and then 3 plus b. Sorry, the multiply is here. And this, of course, does not match anything, so it's going to shift again. And this is going to be x equals term multiplied by 3. And this is the 3. Now, what is the right thing to happen to the 3?
Reduce.
Yeah, reduce it to a factor. So reduce by rule 9. Of course, this is still 3 plus b. And this is going to do x term times number.
Well, why is that 3 plus b since it got moved over into the stack?
3 plus, oh, sorry. Yeah, so here shifting, so there is no 3. OK. So when we shifted, yeah, the symbol can appear only on the stack or in the string. It cannot be in both. Yeah, so that was an error. OK, so now we have the plus, and we reduce the 3 to a number. Then we reduce the number to a factor.
Isn't 3 already a number?
I'm sorry?
Isn't 3 already a number? Because we didn't reduce the a to an ident first. So.
OK. In fact, yeah, this is not even a reduction. So 3 to a number is not even a reduction. So 3 is reduced to a factor. So in fact, I should have written identifier number ID from the beginning, because the parser works with what it gets from the scanner, and the scanner will send it identifier number ID. It will not send it the actual things. OK, yeah. So here it's term times factor plus b. Now the term times factor gets reduced to a term. Reduce to a term, and that's by rule 5. So this is going to be x equals term times factor. So yeah, so this is the term times factor. It gets reduced to a term, and this term will get reduced to an expression. Reduce the term to an expression by rule 4, and this is going to be x equals expression. And now we will do what? We will shift. So now we will shift, and we will shift, which means that we will have x equals expression plus, and that's a b. Then we'll need to shift again. Shift again, and shifting again will give us x equals expression plus b. And expression plus b, then we do reductions. So the b gets reduced to a factor, then to a term. So we have a sequence of reductions. So reduce by 10, reduce 10, and this gives us x equals expression.
But isn't B already an identifier?
Yeah. So by rule number 10, we're reducing an identifier to a factor. And then we reduce the factor to a term, which is by 7. Reduced by 7, we get x equals expression plus term. And then expression plus term gets reduced by rule 2 to an x equals expression. Okay. In fact, we forgot the semicolon, but that's fine. It's not a big deal. We can you can remove it from the grammar. It's not the point here. So x equals expression. With the semicolon you will have a shift. So if you add the semicolon, you'll have this, and then you will shift, and you will shift and get the semicolon. So you will eventually get this and reduce x equals expression. You reduce this to an assignment. Reduce this to an assignment by rule number 1. So x equals, this is an assignment. So why are we doing this? Now here, the derivation is a sequence of shifts and reductions. And some of these reductions, with some of these reductions, an action will take place, and with some of them, no action will take place. So now let's identify the reductions on which an action will take place. So the actual reductions are in which an action will take place are which reductions? Give me
Number node on 10.
Okay, so reduce 10. No, so there is no action because we are reducing by 10. So this is we are creating a node for the identifier. Yeah, so this is so we are doing a make node here for the identifier. Make an identifier node. And on 9, when we reduce by 9, we are making a number node. And when we are reducing by 5, when we are reducing by 5, we are making a multiply node. And this is by 5, this is by, the point is that, reductions like this, for example, reducing by 4, which is substituting an expression for a term, this is not there is no action here. There is no action, so I'm just making a substitution. So reducing by 2 here will result in adding an add node. Make add. Okay, and then we make an assignment when we reduce by 1. So now, how does this work? Well, in the way we do this in practice is that you will write a grammar with these embedded actions in it. These embedded actions will not have pseudocode; they will have C code. So you will write code in C, then that's all what you do. The parser generator is going to generate an LR1 parser for this grammar that you wrote. And in that LR1 parser, whenever it does a reduction according to a certain rule, it's going to generate the code that you wrote for that reduction. So whenever it performs this reduction, it's going to execute whatever code you put in here. And this code, you can put any code that you want. So this can be a line, 2 lines, 1,000 lines. So you control it. You tell it what to do when it performs these reductions. So you are basically saying, OK, generate the LR1 tables for me, and generate an actual parser in C. But in that parser that has the C code in it, whenever there is a reduction by this rule, I want you to execute this code. So you tell it the code that it executes whenever it does the reduction. So then it will do whatever you want. So you control it. It only generates the parser for you. Okay? And in order to do this, you have to think about the actions that you want it to do at for each reduction. You want to think about which of these reductions result in actual actions, and which ones are the ones that will not result in actual actions. So we'll just be passing things up. For example, when you reduce a factor to a term, there is no actual action, so you just pass the information up. You will need to use this $sign notation, and in this $sign notation, the $sign stands for. What does $sign stand for? Well, it stands for the current value, which is the value of the left-hand side of the rule. So $sign is always associated with this symbol on the left-hand side. And the $sign number, $1, $2, $3, they correspond to the symbols to the right. And make sure that you count all the symbols. So this is one symbol. So this is $1. The equal is $2, and the expression is $3. So every symbol count. And a symbol could be a terminal or a non-terminal. OK? All right. So now, any questions on this? So in order to understand this $sign notation, we'll have to give another example. We'll just, in a minute, we'll go through another example that instead of constructing an abstract syntax tree, will compute an estimate of the computational cost of a given computation. We'll see what that means. But before I move to that, are there any questions on this? Yes?
How come there's no action for reduce 10?
There is no action for what?
Reduce 10?
Yeah, you missed it.
Or you just miss it?
In reduce 10? Yeah, there is always an action. So you make an ID node. Yeah. Make ID node. Yeah, for every reduce 10, there is an action. So if we missed that, yeah. So on 4, there is no action. 7, there is no action. 4 and 7 do not result in actual actions. So we just pass things up. OK. So any questions on what's on the board? OK. Now, using the same grammar, we don't necessarily have to use this to construct an abstract syntax tree. We will go through an example right now to understand how this works and how the information is passed up. OK, so assuming that we know the cost of the different operations, so we know OK, so let's Okay, let's assume that the cost of an add equals 1 unit. The cost of a subtract equals 1 unit. The cost of a multiply equals, say, 3 units. The cost of a divide equals 7 units. And the cost of a load equals, say, 4 units. Cost of a store equals 3 units. Now, given these costs, we would like to write embedded actions in this grammar to compute, to estimate the computational cost of a given, of a given string, which is an assignment statement. So this will accept only assignment statements. So in this case, I was going to say, we will say that, okay, we will think about the leaves, because the computation will start from the leaves. So for an identifier here, in order to compute this, we will assume that the code that will get generated is going to load A from memory. So for every identifier reduced to a factor, we will have an embedded action, $$ equals the cost of a load. And the cost of the load is, in this case, 4. So whenever there is an identifier, we're assuming that the generated code will be a load. Now, is this assumption, is this a valid assumption or not? Does it make sense or not in general? What do you expect? We haven't talked much about code generation, but is it a reasonable assumption to say that whenever there is an identifier, it will get loaded from memory?
Well,
If it's already loaded, well.
Yeah.
The problem is, what if you have to do a store?
No, well, store is a different story. But the question is, not every identifier that appears in an expression will get loaded into memory. So, for example, if you have something like this, x equals a times b plus c plus a plus 3 times a plus 7 times a. So the code that will get generated for this is not going to load a, 4 times here.
No.
It's not going to load the a 4 times. It's going to load it once and then reuse it. Okay? But now, well, in order to do something like this, what do you think? How do you think compilers do this? In order to find out whether this a has been loaded or not. Whether we have an instruction that does load a into some register.
In the table.
Yeah, exactly. So we have to track this in a table. We have to track this information in some data structure. And one data structure that we can use, this is the symbol table. So in fact, one of the most important data structures in a compiler is the symbol table. And that symbol table will have all the symbols in it with some with some information. So it will have, in this case, there is A, and there is B, C, and it will have information about each symbol. One of the pieces of information is the memory location. Symbol table. And then you can have memory location. So the memory location is the location of this variable in memory, which is what we care about. And in this you can add is loaded, a flag indicating if this variable has been loaded or not, or is loaded at least in current block. And so if it's loaded, if this is loaded, then we will the cost is the cost of a load. If it's not loaded, then we can say that the cost is 0. So in this case, the code that you can add here, you can add an if statement. If identifier, or if the actual token is loaded, then $$ equals 0, else $$ equals the cost of a load. So if it's already loaded, basically this incurs a search in that table or on some data structure that has information about this particular identifier, whether it has been loaded in this block, because it may have been loaded in another block. Now, don't worry about the concept of a block. We will get to this later, but for now, we want it to be loaded recently and in the current block of code that we are currently processing. It may have been loaded previously in a piece of code that is distant from the current piece of code that we are processing. So it could be too distant, but let's not worry about these details for now. So the idea here is that a variable will not get loaded all the time. Now for this number, we'll do what's the corresponding operation for a number?
Conversion.
Make a number now?
Well, no, we're not building the tree here. So for a number, if an identifier is loaded, we can do a load immediate. Usually it's the compiler does a load immediate for a number. So the cost of load immediate is, say, 1. So here we'll say that, okay, it's $$ is equals the cost of load immediate. Okay, now the interesting stuff. Now what should we do here? The cost of a factor is
Just the cost of the expression.
the cost of the expression, because these are just open parentheses, closed parentheses. And how do we express this? $$ equals. How do we express this using the $ notation? Yeah.
$2.
Yeah, exactly. It's $2. Why $2? Because this is $1, this is $2, this is $3. So you count all the symbols, whether they are terminals or non-terminals. And what's the symbol number of expression on the right-hand side of the the right-hand side of the production? On the right-hand side of the production, there are 3 symbols. Symbol number 1 is open parentheses. Symbol number 2 is expression. Symbol number 3 is close parentheses. Okay. So the symbol that we care about is symbol number 2. Okay. Now when we substitute factor to term, so this is, again, this is a pass action. So we are just saying $$ equals
$1.
$1. Yes. Now what should be the cost of term divided by factor.
Cost of dividing?
Well, that's not sufficient, because if you are dividing, so you have a divide in this tree,
Yeah.
and you have a
Yeah,
dividing a term
yeah,
and a factor.
yeah, you gotta make sure that everything's loaded in the register so you can do the divide.
Well, we are dealing with the term and the factor at this level. We are not at that level. This is the leaf level. At the leaf level, we may load or not load. But at this level, we have a term and we have a factor. So what's the cost of the divide in terms of the cost of the term and the cost of the factor? Because this term can have a whole tree. It can be a huge term. And this factor, by the way, we'll go through a concrete example. And this factor can have a huge tree below it.
Yeah.
So whatever this term is, we want to take its cost and the cost of the factor, and then add to that
The cost of
Cost
the
of
divide?
divide.
the cost of the divide. Exactly. So how do we express this using the $ notation?
It would be $ equals $1 plus cost of divide plus $3.
Yeah, exactly. Yeah, it's $ plus equals $1 plus cost of divide plus $3. So when we are doing the divide, this is $1 and this is $3. Okay. Now, obviously, this is going to be similar. So $, is $1 plus cost of multiply plus $3.
That would mean that the add and subtract would be similar to it too.
Yeah, and these will be similar. Term is going to be $, equals $1. So this is just a pass. We'll go through a concrete example now, and it will become obvious. Our expression, again, this is going to be $, equals $1, which is the expression, plus cost of what? Subtract plus $3. And this is $, equals $1 plus cost of add plus $3. Now what should we write here?
Going to be $3 plus the cost of storing.
Yeah, exactly. It's $3 plus the cost of storing. This identifier is not something that we're going to load, right? So we will store it at a given address. So there is no loading here. So $, is going to be the cost of expression, which is $3, plus the cost of store. So the only thing that requires computation is the expression. Then we will have to assign it to store it at a given address. How will we know the address? We will look up the address for this identifier in the symbol table. And then we will know the address to store to. And finally, in the last rule, what should we write? $, equals what?
Just $1.
$1. Yeah. Okay. So let's trace it. Let's trace it on some example. Okay, should we use the same example or a different example? I think we're done with these. It doesn't. Oh, Wi-Fi. I deleted the numbers, but that's fine. So, yeah. Okay. So now, okay. So let's take this example. X equals A times 3 plus B, for which we have the tree here. So now, with this tree, what will happen is that the first thing that will happen, we will reduce an identifier to a factor. So when we reduce the identifier to a factor, we will calculate the cost of the load. And the cost of the load is going to be, the cost for factor, it's going to be 4. Okay? So this is going to be 4. Then we will do a reduction from factor to term. So when we reduce factor to term, we are just passing the 4 up. So this is what a rule like this means. So this 4, which is the cost of a load, is going to get passed up to this. So the cost of this node, the term, is 4. So this $sign is the value that is associated with a given node in the tree. So in each node in the tree, there is a value associated with it. And this $sign is this value. And these actions define the value of a node in terms of the values of the children of that node. So this is what kind of tree traversal? Yeah. What kind of depth first?
Post.
It's post order. Yeah, because you are defining the value of the current node in terms of the values of the children. So you have to process the children first, then process the parent. So processing parent after children, this is post processing, post order. Okay, so now term is 4. Again, the next step is going to be number, reducing the number to a factor. And for a number, for a load immediate, we said it's going to be a 1. So the 1 is going to be here. Then, when we do this reduction, term times factor, when we do this reduction, the cost, so we are here now. At this point, $sign is this. And $1 is the term. $2 is the multiplication. $3 is the factor. So what we are saying here is the cost of this term is going to be $1, which is the 4. So at this point, $1 is a 4, plus the cost of a multiply. And what did we put there? 3?
Yeah.
For the multiply? Yeah, 3. So it's going to say, OK, 3 and 4 and 1. So this is going to be an 8. So the value for the term is going to be an 8. OK, so this is an important step in this calculation. When this reduction takes place, we calculate the value of the node in terms of the values of the children. So the value of this children is 4. The value of this child is 4. The value of this child is 1. And we add to this the cost of the multiply. So in order to compute this, we need 8 units of computation. Similarly, here the identifier, it's going to be a 4. It will get passed to the factor. And this is going to be, from factor to term, you just pass it up. And from term to expression, when we reduce term to expression, when you reduce term to expression, you just pass up. So you pass the 8 up. So now you have 8 and 4, and you add them.
Which is going to add operation.
The add has a cost of 1. So in this case, you will get a 13. Right? So the cost of computing this is going to be a 13. And again, when you do this, at this point, $sign is the expression. $1 is this expression. This is $2, and this is $3. So when you are computing this expression, the parent expression is $sign. The left-hand child is this expression, and the right-hand side, on the right-hand side you have this expression and the cost of an add, and this expression, which is the cost of the term, which is $3. Okay. So this is here. Now when you substitute, so this is the expression. Then the final step is the store. So this takes 13 units of computation to compute. And the cost of the store, did we put 3 or 4?
It's 3.
3. So 13 plus 3, this is going to be 16. And again, when you look at this assignment, this is going to be your $1. This is going to be your $2. And this is going to be your $3. And in fact, $4 is the semicolon. OK, so so we have a semicolon here, but it doesn't matter. So this is the semicolon is going to be $4. Don't forget any symbol. Here, this symbol does not matter. OK. Yeah.
Question.
Yeah, sure.
Okay, I understand the instruction scheduling part, but why are we computing the cost of each operation? Is that useful later on?
Oh, this is an exercise. Now, this is an exercise at this point. So we're doing it right now in class because it's an exercise that will explain how this works. From a practical point of view, is it ever useful? Yes. So it's sometimes it's useful because sometimes the compiler, even at a high-level representation of the code, may want to estimate the number of operations needed to compute a certain expression or a certain block of code. So it's useful to compute an estimate of evaluating a certain block of code or a certain function or whatever. So for example, at some point I worked on the prefetcher in the GCC compiler. The prefetcher is a compiler optimization stage that adds prefetch instructions to prefetch memory locations before they are needed, so that when you need them, they are already in the cache. And in order to figure out the prefetching in a given loop, now, in order to figure out how early you will need to prefetch something in a certain loop iterations to use it in the next iteration, right? So you want to prefetch a of I plus 1. Well, you are here in iteration I. You prefetch I plus delta. So you need to prefetch something for the next iteration. Now, how far ahead should this be? How should you fetch for iteration number 2 or 3 or 4? This depends on the body of the loop, what you are executing in the loop, and how much computation you expect to happen inside the loop, so that you know whether to fetch 3 iterations ahead or 10 iterations ahead or 100 iterations ahead, depending on how big the loop is. And in order to know how big the loop is, you need to come up with some estimate like this of the operation. So it's not just counting. Counting instructions is not enough because some operations are more expensive than others. A divide is more expensive than a multiply. So yeah, in practice, compilers may want to do this kind of computation. But we are doing it here only to understand the embedded actions and the $ notation. So that's why we are doing it here, to understand how the embedded action and the $ notation work. Any other questions? OK, so, well, OK, so let me then ask you a question. Let's try to do a different question. This same thing. Let's do write embedded actions that will count the number of divide operations. Count the number of divide operations in the expression. So how do we modify these actions? So instead of computing an estimate of the computational cost, we would like to just count how many divides there are in an expression. So if you have an expression like, x equals a divided by b plus 3 divided by 4 plus c times d plus f divided by n. If you have something like this, then you want this to give you the value 3. So if we have an expression like this, we have 3 divides in this. Now, how do you modify these actions to count the number of divides in an expression? So let's go through them one by one. So what should we write here? $sign equals 0. Yeah, this is the leaf. So this is $sign equals 0. For the number, same thing. So these are the leaves. $sign equals 0. What should we write here?
That can stay as is.
It stays the same because the number of divides in this thing is equal to the number of divides in the expression. Okay. Now what should we do here? Same thing. Now what should we do here?
$sign equals $sign plus 1.
Yeah, exactly. So it's $sign 1 plus $sign 3 plus 1. So we can do it this way. $sign 3 plus 1. So the number of divides is the number of divides in this term plus the number of divides in this factor, which may have many divides in it, plus the 1. Okay? So now what should we do here?
Just same thing. Put a 0. So
$1 plus $3.
$sign 1
Plus $3.
plus $sign 3. And that's it.
Yeah. And this
Okay.
for the
So this is we just pass up.
Yep.
This is $sign.
same as multiply.
Yeah. So this is plus $sign 3. And this is $sign 1 plus $sign 3. And this is $sign equals
$sign 3.
$sign 3. Yeah. Okay. So this was a question in the quiz last semester. So let's extend the grammar a little bit. So this is goal equals, no, instead of assign, let's do a recursion on assign. So let's do block equals, sorry, block is an assign or block. Oh, yeah, we have to have 2 rules. So yeah, let's put it here. Block is assign or block assign. So what does this mean? What does it mean?
Block is 1 or more assignments.
Block is 1 or more assignments, or you can have any list of assignments, an arbitrarily long list of assignments. Now in this case, obviously what we write here is $sign equals
$sign 1.
$sign 1. And here, $sign equals, yeah, it's S1 plus S2. S1 plus $sign 2. Why? Because we are saying that, because we are doing the recursion, so we're saying that when we do the recursion, the number of divides in this, in the big block is equal this block times the assign. And what will this block have at some point? So if we have 10 assignments in this block, when we do the final reduction, in the final reduction, this assign is going to be the last assignment, and this is going to have 9 assignments in it.